Hey everyone. In the last scientific critical thinking video, we talked about different methods that are used in physics, different tools that we can use to approach different kinds of problems. Tools like looking at the system in terms of its kinematics, how do we describe that motion? In terms of Newton's laws, or in terms of conservation of energy, or conservation of momentum, or conservation of angular momentum. So in this one, I want to apply this to the upcoming lever experiment and figure out, well, which tools are we going to be able to use, and can we use those tools to build a model of this lever system that can make specific quantifiable predictions of what the outcome of the experiment is going to be, and then we'll be able to say the experiment will allow us to put those predictions to the test. So let's just quickly talk about what this lever experiment is going to be. So we're going to have a horizontal lever, so something that can kind of rotate in a horizontal plane. And we're going to say mass M1 hits this directly, so it's a right angle hit to the lever at one end at a distance of r1 away from the fixed fulcrum point at an initial speed of v0. When this hits, the lever is going to rotate and launch mass 2, which is a distance r2 from the fulcrum point. And we're going to be looking at how fast is M2 being launched, how fast is M1 moving after, what's going to be happening with the rotation rate of the bar afterwards. And again, we want to try to predict how is this system going to act if I use different masses, or if I place those masses at different locations along the bar. So let's see what tools are going to be most useful to allow us to analyze the system to, again, be able to make predictions that we can then put to the test by actually doing the experiment. So let's look at this system first in terms of linear momentum and identify whether we can use conservation of linear momentum to analyze this particular system. The alternative model of this lever experiment that has been proposed by Draft Science is that if you place the objects in such a way that the torques would balance if we hung these masses up and tried to balance this on that fulcrum point. So say M2 is half the mass of M1 but at double the distance. Then in his model, we can use his version of conservation momentum and say that all of M1's original momentum will go into M2. So if M2 is half the mass, it should be launched with double the speed that M1 originally had before hitting the lever. Or if M2 was 1/3 the mass, but at 3 times the distance, it should be launched with 3 times the velocity. Now, this would violate the textbook physics description of conservation of energy, but that's a part of his model, and we're going to be, when we actually do the experiment, we're going to be comparing against this. Which model is more accurate? The standard textbook, physics textbook description of physics, or his model? So what does the kind of standard textbook physics description of this system say about whether we can use linear momentum? Well, the total linear momentum is only going to be conserved in the case where there are no external forces acting on the system. If I have two objects run into each other, if there are only internal forces between things that we say make up that system, that's when we're going to get this conservation of linear momentum. But in this case, when M1 hits that lever, there's going to be an external force at this fulcrum. Otherwise, when mass M1 hits the lever, the entire thing is just going to fall, just get pushed away. So since there's going to be an external force at this fulcrum point during the hit, linear momentum will not be conserved. This is not the right tool to use if we're trying to analyze the motion of this fulcrum system. Okay. So what can we use instead? Well, let's look at this system in terms of angular momentum. The total angular momentum about an axis is conserved when there are no external torques acting, again, around that axis. So the axis that we're going to look at is this fulcrum point. Even if there is a force, an external force, acting at this fulcrum point, the torque due to that force, measured around that fulcrum point, is going to be 0. Imagine trying to open a door by pushing directly at the hinge. You can push as hard as you want at that hinge. It's not going to cause a torque to the door, and it's not going to get that door to rotate. In the same way, if we're measuring our torques and our angular momentums around this fulcrum point, any external forces that are acting here will not cause an external torque. So we can use this conservation of angular momentum. So let's see how we actually calculate this. For angular momentum, if I have a point particle moving around some axis, the angular momentum is defined as the cross product between the vector that points from your axis to where that particle is located, crossed with the momentum of that particle. Now, for simplicity, we're going to just say I'm dealing with rotations just in a plane. We're not going to worry about the full vector version of angular momentum. Other than to just say we can have motions that are counterclockwise around the axis and motions that are clockwise around the axis. So we can kind of simplify this to how far are you from the rotation axis at the closest point of approach times the mass of the object times its velocity. Okay? If I have an extended object, some larger object that's rotating, we can calculate its angular momentum around that same axis by measuring both its moment of inertia, so that's this value I, it's a measure of how much mass is there and where is that mass distributed. If there is more mass further from the rotation axis, so if I'm rotating around some axis, if there's more mass further from that rotation axis, it's a larger moment of inertia. And the angular velocity. So it's the moment of inertia of the object times the angular velocity if we have this extended object that is rotating. And for a uniform bar, well, that bar has some mass. Its mass is distributed around its axis. And for a uniform bar rotating around its center, that moment of inertia is going to be 1/12 the mass of the bar times the full length of that bar squared. So we have a way of calculating. I'm going to make sure I get the masses of any levers that I'm using. I'm going to get their lengths so we can actually calculate what this moment of inertia is. So let's say we're looking at the system before mass 1 hits the lever. Okay. Well, in that case, the only thing that's moving is just mass 1. So we've got the angular momentum of that point particle around the axis. So that's going to be the distance r1 just before it hits the lever times the mass of that object times that initial velocity that it's traveling at before it hits the lever. Okay. So that's how much angular momentum we start with. Afterwards, well, mass 1 might be moving. For now, we're going to say if it's moving down, I'm going to continue to call that a positive velocity. If it bounces back up, I'm going to call that a negative velocity. This lever is going to be rotating with some angular velocity. And this lever has also launched mass 2. So mass 2 is now going up. And this velocity 2, I'm also going to call this a positive velocity if this object is going up, because all of that is associated with a counterclockwise motion. If m1 is moving down, that's counterclockwise around this axis. If this lever is rotating counterclockwise, we've got that counterclockwise motion. And if this mass 2 is moving up on this side of the rotation axis, that's again getting us our counterclockwise motion. So that's what I'm defining as my positive direction. So if we take these objects, well, m1 might have some angular momentum. Again, that's at distance r1 times m1 times v1. Object 2, mass 2, is at a distance r2 times m2 times v2. And we've also got the moment of inertia the angular momentum of the bar. It's moment of inertia times that angular velocity. Okay. So, since there are no external torques acting on this system, we have conservation of angular momentum, which means I can put these two equations together and say that in total, for any of these collisions, I should have conservation of angular momentum, where r1 times m1 times that initial velocity before the hit is r1 times m1 times v1 plus r2 times m2 times v2 plus the moment of inertia of the bar times that angular velocity. Now, this is making some assumptions. We're assuming that the fulcrum itself has very low friction, so we're not getting any external torques due to friction. But again, as long as there are no other external torques acting on our system, which we should be able to control for to a pretty high degree of accuracy, then this conservation of angular momentum equation should hold for all of these collisions. So this should be satisfied in all cases, but there is a problem with trying to use this angular momentum alone. Because we can say, I can pick my R1 and R2 values, I can pick the mass values, M1 and M2, I can pick how fast, or at least measure how fast is that original object being thrown. But we've got one equation with 1, 2, 3 unknowns. We don't know what the final velocity of object 1 is, we don't know the final velocity of object 2, and we don't know the angular velocity of that bar afterwards. So if I want to actually be able to make specific predictions for specific cases, we need a little bit more information in order to get this to work. Okay? We need to know something about what type of collision are we dealing with. The objects that are hitting, are they elastic objects that are going to bounce off and maybe do a better job at conserving kinetic energy? Or are we going to get an inelastic collision where the object kind of sticks to the lever afterwards? So in order to get more specific than this, again, this conservation of angular momentum should be conserved, should be holding true in all of these cases. But we want to make sure we know what else also has to be holding true. So let's start with the inelastic case. So I'm going to say we're going to work with a case where M1 sticks to the lever, so that would be an inelastic collision, and M2 is launched with a velocity matching the tangential velocity of the bar with ideally no flexing of the bar. Are we going to actually be able to get no flexing of the bar? That's probably going to be a bit of an assumption, but we'll again talk about that as possible sources of error a little bit later. So if we have these assumptions, well, we've got some additional conditions. If M1 sticks to the bar, then that angular velocity should be related to the velocity that this object has after the collision and how far it is from the rotation axis. Because again, this object is sticking to the bar, its linear velocity and how far it is from the fulcrum point is going to be related to how quickly is that bar rotating. Same for V2. If the V2 is being launched with a velocity matching the tangential velocity of the bar. So again, V2 isn't elastic. It's not going through its own kind of bouncing motion. It's just being pushed by that bar initially. Then that angular velocity should also equal V2 over R2. And notice we can also relate V1 and V2 directly together. So V2 is just going to be R2 over R1 times the velocity of object 1, again, after the collision. So let's take these conditions and plug them into our conservation of angular momentum equation. So if I sub some of these in, I can replace V2 with R2 over R1 V1, and I can replace this angular velocity with V1 over R1. Okay, so that's all I've done here. And I'm not going to go through all the algebra steps. Again, there's going to be some algebra steps that I skip in here. If you want to see me make a video with just lots of algebra steps, I can do that. But at least this one, the algebra isn't too bad because I can just factor V1 out of all of these terms. I think I also multiply both sides by R1 just to get rid of this, some of these R1s in the denominators here. But we can basically rearrange and solve for V1 in terms of where is M1 hitting, what is the mass and the R distance for object 1, what is the mass and the distance for object 2, and what was the initial velocity before the collision. We can also have the moment of inertia of the bar added in here as well. So again, these equations, they look kind of long and a little bit ugly at the beginning, but we have all of the information where if I know how fast this thing was launched, I can predict how fast object 1 should be moving after it hits and sticks to the bar, and how fast object 2 should be moving after it's launched by the bar. We can look at some particular cases. So again, these are just the two equations that we just derived. And for this one, let's just look at a couple of cases saying we're going to assume that the bar's moment of inertia is fairly small, like assuming a low mass bar. Well, we can make some predictions. If M1 and M2 are the same and those distances are the same, and you plug that information into these equations, well, V1 will be half the initial velocity that it was moving at, and V2 will also be half of the initial velocity that M1 had as it was coming in just before hitting the bar. If we say, well, let's do the case where M2 is half the mass, so M1 is equal to 2M2. So M2 is half the mass, but at double the distance. Well, if we have this inelastic case, object 1 should be going at 1/3 of its initial velocity, and object 2 is going to be launched at 2/3 the initial velocity of object 1. Remember, the alternative model that was being proposed is saying, oh, V2 should be launched with twice the speed that mass 1 originally had before hitting the bar in this particular case. That's nowhere near what we're getting for this prediction, so we have different predictions for what should happen to this system. We should be able to gather data and look for which model is better at predicting the motions of this particular system. If we say, oh, let's do the M2 is 1/3 the mass, but at 3 times the distance, well, we get different predictions for the velocities of object 1 and object 2 afterwards. And again, these are cases that we are going to be testing. Okay? So again, right now, these are predictions, and we should withhold either accepting these predictions or rejecting them. We should withhold judgment entirely until we actually do the experiment. Okay? But one of the things in the alternative model that has been proposed, there was this requirement that it always has to be in this balanced state. If M2 is half the mass, it's got to be at twice the distance in order for Draft Science's model to be able to make predictions. At least I haven't heard any other kinds of predictions. But this model says you can set the masses to be any values, and you can set them at any locations. So if I just did M2 is half the mass, but they're both at the same distance from the fulcrum, so it's evenly spaced around the fulcrum, we can predict how fast are those going to move. They should both be moving at 2/3 the initial velocity. If I said the masses are the same, but object 2 is at twice the distance, well, we should get 1/5 and 2/5 of the initial velocities for objects 1 and 2 respectively. We can again make specific predictions, and these are more cases that we're going to be testing. To make this a little bit easier to work with, I've actually put together, and this is going to be something that we use in the when I actually do the data analysis, I've put together a quick little Excel document that actually goes through these calculations. So if I have everything same masses and same distances, then what these ones are calculating is what happens in this inelastic case. Notice this equation here, hopefully you can kind of see it decently on this on the video. We've got the R1 squared, so that's cell B3 here squared, times B1 for mass 1, divided by B3 squared, so R1 squared times mass 1, plus R2 squared, that's this cell, times M2. And it also takes into account the effect of the bar. So we're actually going to be able to incorporate into this model what about the fact that the bar is not necessarily a completely negligible mass. So if I add in the moment of inertia of the bar, we can see how those predictions are actually going to be updated. Again, I don't think the alternative model has any mechanism that, at least I've heard, of being able to make these kinds of predictions and being able to improve on these kinds of predictions. So I'll set that back to 0. So again, just kind of comparing with some of these other cases, we said if m2 is half the mass, but at twice the distance, then the initial velocity should be the velocity of object 1 should be 1/3 the initial velocity. The velocity of object 2 should be 2/3 the initial velocity. Again, these are just saying initial velocity is 1. It's just a factor comparison. If I go to 1/3 the mass at 3 times the distance, well, there's our 1/4 and 3/4 values. And if I do half the mass at the same distance, so half the mass at the same distance, again, we can make these predictions. This is the 2/3 value. They're both at 2/3. And if it's the same masses at twice the distance, that gives us our 1/5 value and our 2/5 value. So again, these are things that we're going to be actually doing when we actually get the data for the experiment and be able to incorporate in what is the effect of the bar as well. But this has all been in the case where the object 1 stuck to the bar. That's not the only case that can happen. There are other cases. So let's say I've got a new case where M1 is an elastic object. When it hits the bar, it can bounce off of that object. It's like a rubber ball. And M2, we're going to say for M2, we're going to do the same thing as last time and say M2, it doesn't deform. It's not like I've got another elastic ball on the other side. It's just going to be pushed by the bar, and we're assuming, again, no flex for the bar. Again, these assumptions are things that are not going to be exactly matched, but we should be able to get pretty close to having these kinds of conditions. Okay. Couple of things to note. If M1 ends up bouncing backwards, then this velocity would end up being negative. We're still saying for M1, down is the positive direction that we're going to call for velocity because it makes that counterclockwise motion, and up is the positive direction for velocity 2. So if M1 bounces back, that just means V1 is going to be negative. Since we're launching this mass the same way, we can still say that angular velocity is related to the velocity of object 2 and that R2 distance. And we can again apply this to our conservation of angular momentum equation. So if I say that this angular velocity is V2 over R2, I can replace that angular velocity in this equation. And to simplify the algebra a little bit, I'm going to combine some terms because notice we've got a V2 on both of these terms. I'm going to factor that out, do a little bit of rearrangement, and say that my conservation of angular momentum equation becomes R1 M1 V0 equals R1 M1 V1 plus R2 times this value of A. This is the mass of object 2 times the moment of inertia of the bar divided by R squared, and then times V2. Okay. This method of saying I've got this combination of terms and I'm just going to switch that for a new parameter. This can be a very, very useful method of simplifying the algebra. I'll probably do another video on just this method of trying to simplify algebra by having, you can kind of think of this as the effective mass of the object, of object 2, saying I'm also taking into account the effect that the bar has on how object 2 is going to move. But with that in play, what other equations? Because we still have 2 unknowns in here. Well, if M1 is colliding elastically and we don't have any deformation in M2, we should be pretty close to having conservation of the kinetic energy of the system. Again, there's still probably going to be some vibration in the bar itself, but hopefully we'll get pretty close to having an elastic collision. So if that's the case, we can take our equation for conservation of energy. Before the collision, we just have the kinetic energy of object 1 with that velocity before the collision. Afterwards, mass 1 is going to be moving, it's got some kinetic energy. Mass 2 is going to be moving, it's got some kinetic energy. And the bar is also going to be rotating. even though the center of mass of that bar is still fixed in place, all those moving parts mean that this object has kinetic energy. This is the equation for the rotational kinetic energy of a purely rotating object, an object that is just rotating around some axis. Well, one thing that we can do with this is actually simplify it again using this exact same factor that we had in the previous equation for looking at conservation of momentum. And say that, well, if I have this m2 times the moment of inertia of the bar divided by r2, we can combine these particular points. Again, I'm also using that this angular velocity is the velocity of object 2 divided by r2, and that's where this r2 squared is coming in. Again, I do encourage people to try to go through the algebra for this on your own. If you want me to go through the entire algebra and do a video on that, let me know in the comments. I just thought we'd try to keep it. It's already going to be a long video, so let's keep going with this one. So we have this equation for the conservation of kinetic energy, and we also have an equation for the conservation of angular momentum, again, around that axis. And now we have two equations with two unknowns. So we can solve this algebraically. It does take a fair bit of algebra. Again, if you want to see the algebra, let me know in the comments and I'll do another video kind of going through these steps. But basically, we can derive two new equations for what's going to be the velocities of objects 1 and 2 after the collision in terms of the two masses, m1 and m2, the two r distances, r1 and r2, and the moment of inertia. This capital A term includes that moment of inertia of the bar. So once again, we have a tool that we can then use to predict how the objects 1 and 2 are going to be moving after this collision. How is it going to be launched? So let's again look at a couple of cases for this. So again, here's our summary equations for this elastic case where m1 is acting like a bouncy ball and hits it, and m2 is just being pushed forwards and there's no flex in the bar. So again, a couple of assumptions there. We'll see when we do the experiment how accurate those assumptions were. But again, for this calculation, let's say that the moment of inertia of the bar is small, so we have a relatively low mass bar compared to some of the other masses that we're using. If we have the case where the masses are the same and those r distances are the same, then object 1 should completely come to a stop. Like, the bar is still going to be moving, but m1 hits and completely goes to a stop and just launches the bar, and that other bar launches object 2 at exactly the velocity that object 1 had beforehand. And you can kind of trivially see that if the bar has no mass and we had a certain amount of kinetic energy coming in, because it had a certain velocity, the masses are the same, the velocity after didn't change, we still have conservation of energy in this particular case. For the other ones, you'd have to go through a bit more calculation to confirm this. Again, I encourage you to try that. So if we have m2 is half the mass, but it's at twice the distance, well, then object 1 should actually bounce backwards a little bit at a third of its initial velocity, and object 2 will reach 4/3 of the initial velocity of object 1. So again, even though this elastic case launches this with a higher speed, it's still nowhere close to that double the original velocity of the object. And again, we can look at other cases. If m2 is a third the mass, but at 3 times the distance, well, the launch velocity of object 2 should be 3/2 the initial launch velocity, or the initial velocity of object 1. And we can again do this in cases where it's not the balanced fulcrum case. So if m2 is twice the mass, if m2 is half the mass, but both objects are at the same distance, we can again predict how fast these objects should be moving after the collision. And again, we can use this same feature. Again, I did this for the elastic case as well. So if I move this down here, this elastic case, it's actually measuring r1 squared times m1 minus r2 squared times m2, times a. So I did this calculation of what a is equal to, the m2 times the moment of inertia of the bar divided by r2 squared. Basically, we are able to kind of go through this and calculate both the velocity of object 1 and the velocity of object 2. So again, just to kind of verify that this is working, if we set everything equal to begin with, then object 1 stops, object 2 just gets launched at the initial velocity of object 1. If I have m2 is half the mass at double the distance, well, there's our negative 1/3 and our positive 4/3. If it is m2 is a third the mass at 3 times the distance, well, there's our negative 1/2 and our positive 3/2. And then again, we can look at this in other cases where m2 is half the mass, but it's at the same distance. There's our 1/3 and 4/3. Again, we can go through these different cases and identify these different properties. Again, these are all predictions, but these are predictions that we can then go out and test. So that's what we're going to be doing in one of the next videos. I do want to apologize that it's been a little bit of a delay in actually doing the lever experiment itself. It's been a combination of getting a bit of equipment and also just, life things taking place. And I did want to make these videos on which methods are going to be the best tools for the job in physics in general, for different kinds of questions, and going through these details on how the textbook model of physics would actually make different predictions about how this lever experiment should go. So those are the predictions, and again, I should be able to actually get the lever experiment done and recorded and posted next week. It's the week between classes for me, between terms for me, so I should have a little bit more time to work on that. But we'll call that good for today. As always, if you have questions about any of this, you can put those into the comments. People responding to comments always try to be, helpful and courteous to others, and we'll see you in the next video.